Okay, today we're going to be talking about exponential and logistic functions, two more of our main parent functions that we learned at the beginning of the year. So let's just jump right in here. We have all exponential functions can be written in the form f of x is equal to some number a times b to the x. Now let me just talk a little bit about what these letters a and b represent. The letter a is the initial value. In other words, it is the value when x is 0, or maybe you could say it is the y-intercept. Let's write that in there, the y-intercept. Let's see if that's true. F of 0 is equal to a times b to the 0. We know that anything to the 0 power is just 1, so a times 1 is a. So f of 0 is a. So from now on, when we ask you what is the initial value or the starting value or the y-intercept, all you have to do is look at a and you've got your answer. Now b is what's called the growth factor. If b is greater than 1, then this is going to be a growth, exponential growth. If b is less than 1, then this is going to be an exponential decay. All right? So essentially, it's going to either look like this. Okay, so let me just illustrate. It's either going to look like that, or it's going to look like this. All right, and we'll get into the graphs in just a moment. So let's just see if we can identify the initial value and the base of the following functions. All right, 3 to the x. You may be tempted to say that the initial value is 3, but you have to hold off on that. You have to recognize that this is really 1 times 3 to the x. All right, now 1 is going to be your a. So that's going to be your initial value, or you could see this as 3 to the 0, which is 1 times 1. So your initial value, so I'll say IV, is equal to 0. Your base, or your growth factor, let's just call it the base, is going to be your b. It's whatever is raised to the x, so that is 3. Okay, now letter B, it can be a little tricky because in order for you to identify the initial value and the growth rate, you have to get it in the form a times b to the x, not to the negative x or the 3x or the 5x or the negative 2x. It must be x. So let me circle that. You've got to get it in terms of x. Now if you notice here, this is negative 2 times 4 to the negative x. So what we need to do is we need to rewrite this as negative 2, 4 to the negative 1 to the x. Now let me just make sure everybody is clear on what I did here. I have a negative 1 raised to an x. Anytime you have an exponent raised to another exponent, the rule is that you multiply those exponents. So I still end up with 4 to the negative x if I have 4 to the negative 1 to the x. Now, if we have a negative exponent, what that means is we need to write it as 1/4. All right? A negative exponent means simply to move the number to the denominator. So, now that we have it in terms of, let me circle it, x, we are able to identify the initial value. There's our initial value. And that's going to be negative 2. And the base is now going to be 1/4. And is that less than 1? Yes, it is. So that means that this is going to be an exponential decay. Hey, we knew that because we learned about transformations a few weeks ago. And what happens when you replace an x with a negative x? Well, it takes the normal parent function that looks like that and reflects it across the y-axis. So that way it looks like this. So that's what it's going to look like. All right, letter C. Once again, we cannot have 3x. We have to convert it. So 7 times, let me do this in white, 7 times 2 to the third to the x. All right, 2 to the third to the x is really 2. 3 to the x is 3x. So this is going to be 7. And then 8 to the x. So my initial value is 7, and my growth rate, my base, is 8. Okay, now we want to find an exponential function from a table of values. So essentially we want to find three functions here. We want to find g of x by using these y values and these x values. We want to find h of x by using these same x values, but now using these y values. And then we want to find an equation for f of x by once again using these same x values, but now using these y values. So I want to make sure the table does not confuse you at all. Okay, so we want to write the formula y equals a times b to the x. And remember, this is my initial value, and this is my growth factor. All right, so let's just see if I can do the first one, and then I want you to pause the video and see if you can do h and f. So g of x, what is the initial value? Well, the initial value is the value of the function when x is 0. So we go over to x is 0. We go over to the y value that is under the g of x column, and that's 4. So we know that this is going to be 4 times something. Now the growth factor. What is 4 being multiplied by to get to 12? Oh, 3. And what is 12 being multiplied to get to 36? 3. All right, and you can see that it's going to be the same here and here. So we can see that this is going to be 4 times 3 to the x. If you're not sure, let's see if we can plug in a couple of values. Let's plug in 2. All right, let's take 2, plug it into the formula. What is 3 to the second power? That's 9 times 4. That's 36. Bingo. All right, so you can see that it works. I want you guys to try h of x and f of x. Okay, h of x. What is the initial value? So now I'm going to look at 0, and I'm going to look at 8. All right, so maybe I'll do this one in yellow. All right, so I'm going to look at 8. So my initial value is going to be 8. And now what is the thing I'm multiplying by? Well, to go from 8 to 2 is not 4, but it's 1/4. All right, so I'm multiplying by 1/4. And you can pick any two numbers, it will work. 32 times 1/4 gives me 8, so on and so forth. So that is my growth factor. All right, let's look at the third one here. F of x. Well, my initial value is going to be 1/2. So f of x is going to equal 1/2, my initial value. And then I have to think about what I'm multiplying by. Well, 1/2 times 3, let's just test that out. 1/2 times 3 over 1 is 1 times 3, and 2 times 1, bingo. So times 3. Oh, you don't trust it? Okay, let's try it for 3 halves. Times 3 over 1, 3 times 3, top times top is 9, bottom times bottom is 2, bingo. All right, so my growth rate is 3. And there you have it. Okay, just like in any unit, we also have to review our transformations. And so we have a parent function here, 2 to the x. And we want to talk about how to transform that. And so we have 2 to the x minus 1. Well, this one's a pretty easy one. We recognize that x minus 1 is really a shift right 1 unit. So that's pretty much a no-brainer there. All right, so let's go on to the next one. 2 to the negative x. Well, if you remember, as I said earlier, when you replace the x with negative x, that is a reflection over the y-axis. Now remember, it would be a reflection over the x if I multiplied the outside by a negative. But it's with the x. So letter C, that's the one that's got all the transformations in it. So let's list them in order. If you can remember that the first thing you always want to list is the right and left shift. So x minus 1 is going to go right 1 unit. And then secondly, we have a 1/3 x. Okay, that is going to be counterintuitive because it is with the x and it's horizontal. So that's going to be a horizontal stretch by 3. This is a good review. We've done everything up here, so now we go out here and we do times 3. That's going to be a vertical stretch by 3. And then we have down 4. So down 4 units. Okay, let's switch gears now and talk a little bit about logistic functions and their graphs. Let's talk about the difference between an exponential function and a logistic function. Exponential functions, it says exponential growth is unrestricted, meaning it has no restrictions, has no bounds. So it looks something like this, all right? It doesn't have an upper bound. It goes on forever. So let's say I put a bacteria in a petri dish and it doubles every minute. All right, it's going to keep doubling and doubling and doubling and doubling and doubling and doubling and doubling, and it's never going to stop doubling. All right, but for a lot of situations, we don't want something that has unrestricted growth. We want things that may start out growing quickly, but eventually level out. For those things, we need a logistic curve or an S-curve. Let me give you a few examples. Plants can only grow so tall. You plant a seed and it grows pretty quickly at first, but then it levels out. Humans can only grow so tall. We grow quickly, and then after about 18, 19 years, we level out. The amount of space in a park for bears or animals, they may put bears or animals in the park at the beginning, and then after a while, there's just not enough space or resources to handle all of the bears or the animals, so it levels out. For situations like this, we need to use a logistic curve to model the behavior. And basically, the logistic functions are going to look like this for the most part. You have a c, all right, over 1 plus a times b to the x. So let's see how we can use this in the problems below. Way, the letter C is the limit to the growth. So that tells you what the growth is going to level out at or max out at. All right, here we have f of x is equal to 8 over 1 plus 3 times 0.7 to the x. And we want to graph these functions and find the y-intercept and the horizontal asymptotes. Okay, the y-intercept, as we know from previous lessons, is always the y value when x is 0. So let's see what that is. When you plug in 0 here, you have 0.7 to the 0. That's 1. Now make sure you don't raise the 3 to the 0. 3 is not being raised to the 0. It's only the 0.7 that's raised to the 0. So 0.7 to the 0, that's 1. So you're going to have 8 divided by 1 plus 3 times 1. That's going to be 8 over 4, that's 2. So we can put a y-intercept here at 0, 2. 8 is the limit to the growth, so that's going to be your upper horizontal asymptote. So that's going to go right here at 8. And the lower asymptote is always going to be 0. Always going to be 0, unless this function is somehow shifted up or down something. If it's shifted up or down something, then obviously both of these asymptotes would move up or down. But if it's not, then you can assume that the lower asymptote is always 0. And from there, it's pretty simple. Just make an S-curve. So it's going to start here. It's going to look like that, and that's an ugly, ugly graph. Let's see if I can draw that a little bit better here. It's probably not going to be any better here. It's a little better. So this is a basic S-curve. All right, let's try the next one. The y-intercept would be when I plug in 0 for x. So negative 3 times 0, let me write this out. 20 over 1 plus 2e to the negative 3 times 0. Negative 3 times 0 is 0. E to the 0, just the e, is 1. Times 2 is 2 plus 1 is 3, so 20/3. All right, now let's just see what that number is. If you make that into a mixed number, it's going to be 6 2/3. So that's going to be my y-intercept, so I'll put that point right there. And my upper asymptote is going to be this number, 20. So I'll put that up here. And my lower asymptote, as I mentioned, is always going to be 0. And so that's really all that you need to find for these, essentially, is the two asymptotes and the y-intercept. And then from here, we just graph it. We make an S curve. We get closer and closer to the asymptote. And there you have it. All right. It's going to max out at 20. It'll never reach 20, but it'll get closer and closer to 20. By the way, let me write these asymptotes out here. This upper asymptote is going to be the line y equals 20, and the lower one will be the line y equals 0. And for this one, the upper asymptote will be y equals 8, and the lower one will be y equals 0. Okay, last problem here. Based on a recent census data, a logistic model for the population of Dallas, T years after 1900 is as follows. All right, so this is basically a model to represent the number of people who live in Dallas after 1900. So you have to remember that T is the number of years after 1900. According to this model, when was the population 1 million? So basically what we're trying to find here is when is this function 1301,642 over 1 plus 21.602 e to the negative 0.05054t. When is this equal to 1 million? What year? What time? And so for this, we need to transition over to our calculator. Okay, I've got the formula plugged in here. And so I'm going to go ahead and hit enter. I'm going to graph it. Obviously, nothing comes up on our screen yet. And we also need to graph the line y equals 1 million. And so we want to go ahead and graph that one. So 1 million, actually let me just write it in there. So that one's there. And of course we don't see anything because we need to adjust the window. Now make sure you understand that in most situations this year, we're going to have what's called first quadrant graphs. In other words, the second, third, and fourth quadrants don't make any sense to use them because they involve negative values of some sort, whether it's x or y. Remember, x here represents years after 1900, so you don't need any negative numbers. So I'm going to put 0, and hey, we're in 2014 now, so I'll just put 120 years. So you have to think about what these letters mean and not just plug in random numbers and not do zoom fit or anything like that. All right, y represents the population of people in Dallas. Well, you can't have negative population, so that's 0. And then the maximum, well, we know it's at least 1 million. Well, actually, we know it's 1,301,000 or so. So we're going to make this 1500 and then 000, so 1.5 million. And because we know what these things mean, we don't have to plug around and play around with the numbers forever. We get a nice clean graph. Now all we need to do is now find the intersection. So we're going to go ahead and do analyze graph, intersection. We're going to do left bound, right bound, and bingo, we have it. 84.5. Now that doesn't mean the 5th month, that means in the middle of the year, 1984. So our answer to this problem would be middle of 1984.